Okay, good afternoon. Just to wrap things up, firstly, we're going to move on to shear today, and I understand that Lucas has done part of this topic before. We're probably just going to be going into a bit more detail with a bit more examinable content when it comes to shear. After that, we'll be going on to virtual work, and after that, we'll be doing the last topic, which would be the flexibility method. So if you wanted one of these, in terms of these parts, do remember that you can collect them from the technicians at the MDLS. I think instructions have been sent out, so just follow those instructions and just turn up on campus, and you should be able to collect one of them if you wished. The other thing to talk about is the final exam for the buckling. So the TAs have created video solutions of the previous year's questions. You can see from the previous year's questions that they've effectively been taken from some of the advanced or exploratory or basic questions in the course book. So if you've done all of those, there should be nothing for you to worry about. So we've got video tutorials which have been uploaded onto the Dropbox, and that would cover the 2019 question. It would cover the 2018 question too. It would cover these questions here. Have a look at the marks. You can see that one's worth 10 marks, so that's a pretty easy question that can be done in about 5 lines, identical from the identical to the problem sheet BC B6. When we've got more difficult questions, they're worth less marks. So you can see that's a 5-mark question, even though that question is a lot more difficult than that question. So there's nothing to stop you from getting an A grade. If you can't, even if you don't wish to study to get these 5-mark questions. So we'll see here again 10 marks for here, which again is probably just a 5-line calculation, and then probably a lot more calculation is required to get the extra 5 marks for the exploratory or advanced level. So don't worry too much. Just make sure that you can go through most of the questions in the course book so far, and if you feel you can't do an exploratory question for any reason, don't worry, it's not going to stop you from getting an A grade in this course. So we'll now move on to the next section in the course book, which is shear stresses and beams. So I'm aware that Lucas has covered some of this. Just to give you some background, I used to cover all of this in this course, but since it's stated in your syllabus that this will be covered, we have to cover it. Last year, Quincy started to do the shear, but he didn't finish the shear, so I finished it off, even though that required a recap. I spoke with Lucas this morning, and he's done some shear, but he's quite happy for me to go through the shear again, just to give you some additional reinforcement. So given the fact that Lucas has covered it already, I'll go through it pretty fast, but if you need more information and go back to Lucas's notes, I can also release last year's lecture recordings to anyone who wants. If so, just let me know. So, shear stress and beams is the next topic. Remember that the course notes and also the course questions, so all of these questions that have been taken here, broken up like the buckling into the basic, advanced and exploratory questions. Remember that all of these have been taken from textbooks. And also the lecture notes have also been taken from textbooks. So the textbook that it's been taken from is Megson, which in my opinion is the best textbook anyway. So it's been taken from Megson, and you would be able to download the Megson textbook from the university library if you wish to. So that's that basically just tells you where the content has come from. And if you did feel you wanted to read the textbook with a bit more detail, then Maxon, in my opinion, is the best one to go to. Prerequisites for the shear, of course, concept of free body diagrams, concept of equilibrium, concept of calculation of shear forces and bending moment diagrams, concept and calculation of section centroids, and normal stresses due to the bending moment. So the normal stresses due to the bending moment is just sigma equals my over I, where m is the bending moment, y is the distance from the centroid, y is the distance from the centroid of the section, and I is the second moment of area or moment of inertia. Concept of properties of the centroids for the first and second moments. Again, just go back to the start of the course book, and if you had a look, it's a bit like the buckling, where you need to know how to calculate second moment of areas. Just make sure that at the very minimum you're able to calculate IXX, IYY for this section here, and identify which one is the major or the minor axis. And while we're on that, I would say that when we move on to virtual work, you will need to be able to revise how to use method of sections and method of joints. So again, all of that is in the course book there, and also in the Zoro Q exercises. So, table of contents, calculation of shear stresses, concept of shear flow, and then we'll talk about the thin walled sections again, and talk about the shear center in those thin walled sections. So we sort of introduced a thin walled section in the buckling part of the course. So remember, if you've got a circular section like there, you can just use the center line dimensions, and there will be appropriate equations provided for thin walled structures, or structures that are thin walled in nature. So that one, if it was, you could use the exact or the thick wall theory to calculate the area, or you could use thin walled assumptions. And thin walled assumptions, as we've seen, they become very, very close to thick walled numerical numbers as the sections become much thinner. So here I've drawn in the dotted line the midline dimensions, and if you're working off the midline dimensions, then you're using thin walled theory. And later on we'll see a channel section, so I'll draw a channel section like that, and Lucas said he sort of covered that already. And then if we were looking at the equivalent thick walled, it would look something like that. So thin walled theory just allows you to make use of the center line dimensions, which reduces the calculation effort. And in any case, we're saying that if something is very thin, it's going to have no transverse shear stresses. So we're making an assumption that there's no transverse shear stresses in that direction, which reduces a lot of the calculation burden. If you're wondering, thin walled assumptions or thin walled sections or thin walled assumptions is generally what you'll be using when you go to industry, for the specific reason that it reduces the calculation effort by making the assumption that you've got no transverse shear stresses. So in effect, it's saying out here you've got the atmosphere, here you've got the atmosphere here, so there can be no variation of shear stresses in that direction, no variation of shear stresses in that direction, and no variation of shear stresses in that direction. And we'll be recapping that later on. So where do we start? External loading of beams and frames cause internal stresses consisting of bending moment, axial forces, and shear forces. So we all know that when you've got a simply supported beam with a point load there would be a reaction there, a reaction there. You'd be drawing your shear force diagram. I'll just draw the your shear force diagram would be looking something like that. And then if we took an artificial cut going through here, And if we took a free body diagram of what's going up there, then we would see that on this side of the cut there would need to be a vertical to be in equilibrium with the reaction, and on the other side of the cut that I'll draw further away, there would need to be another shear force. So these two are equal and opposite, of course. So when you make your cut, make a cut there to the left side of the cut for this simply supported beam, the shear force is going downwards, and to the right the shear force is going upwards, so that when you remove the cut, the two obviously have to cancel each other out, otherwise your structure is going to be moving. So when we talk about shear, we're talking about, I was going to use the word flow, but that's wrong. We're talking about the actual shear distribution of the section. So yes, we can get our shear force. If that was 10 kilonewtons there, let's say 10 kilonewtons there, and the load was at the center, so we would know that on either side is 5, then here we would have 5 kilonewtons for the shear forces down to the left and up to the right. But that says nothing at all about the distribution, sorry, that says nothing all about the cross-sectional area. So if we set that's section AA, we've not said whether it's that shape, we've not said whether it's that shape, we've not said whether it's that shape, we've not said, or another example could be a circular section like that. So we know the shear force, which we can always get from the shear force diagram, but the shape of the section will affect how that shear is distributed. So we talk about the effect of shear force on structural members, especially the distribution of shear stresses in the cross section. Although not true in all cases, the effect of bending moments tends to be more demanding on the member than the effect of shear force. So generally you'll be designing a section for bending and then you'll be doing the shear check, leading to a tendency to design for bending moment and its associated effects, and then check the shear capacity is not exceeded. So that's what I was doing when I was in a design office. This is typically the case for steel and timber. Reinforced concrete beams do require to be designed for shear, and the main effects of shear are to calculate shear stresses. Placing increased demand on the material of the beam, shear strains result in an increased deflection. But for typically long beams, this is very small. So what this means is that when you do a Google search and you try to find equations for deflections, so for example, you could have a simply supported beam under a point load. You can type into Google what is the deflection what is the central deflection under a load 100 kilonewtons, and it will tell you what an equation is. That equation, important point to note, only refers normally to the bending component. So there's a shear component of deflection. So you later on in the next section will be drawing the bending moment of that, and we'll be using the bending moment diagram to work out the deflection due to bending, and we will also be drawing the shear force diagram of that, and then we'll also be calculating the deflection to shear. The deflection due to shear is many times smaller in most cases than the deflection due to bending, and so we normally ignore it. But it's important as an engineer that you recognize that you're making an assumption that our equations that we use to calculate our deflections normally ignore the shear component, or normally ignore the deflection due to shear. So hopefully that will become clearer later on. So up here we see the direct or normal stresses produced by a bending moment. So that would be the bending moment there, and that would be the distribution of stresses. Stresses produced by the bending moment have this triangular distribution, as you already know. Also, when you've got an axial force, that would be the axial force. The well-known formula to calculate these stresses is when you want to work out the stress, you take the axial force divided by the area to give you a stress, and then you would add on the bending component depending on where you were. So if you were wanting to work out the stress at the neutral axis, then obviously then that bit would become 0 because you're working out the stress at the neutral axis. But if you're working out the stress up here, then the bending stress can be quite large compared to the axial stress. Right. So in this formula, A is the cross-sectional area, I is the second moment of area, which we've calculated, and Y is the distance from the neutral axis. So here would be the neutral axis of the section, and that's where we would be setting our Y axis. So when we say what the distance Y is, it's relative to the neutral axis, which is where we are sticking our axis, or assuming that it starts from. So from figure 1c, we can see that this is the shear distribution. So this is bending, here this is axial, and then here this is shear. And you can see that the shear acts down the face. So from figure 1c, it's obvious that the shear force V, so simply supported beam, point load of 10, reaction of 5, the shear force is 5. It's obvious that the shear force gives rise to transverse vertical shear stresses. So in total, so if you integrate over this, you're going to get 5 for that example. But we've not said anything yet about the distribution. Let's talk about the distribution. We know that this is the atmosphere, so there's going to be air here and there's going to be air up here. So that's the atmosphere. So the shear stress here has to be 0. The shear stress here has to be 0. And later on we'll show that the shear distribution is going to be parabolic. But you should already know that from what Lucas has taught you already. So we're just saying that the shear distribution is not uniform, and is not going to be constant, and it's actually going to be a parabola, which we can prove, and it's going to have a highest value here. So from figure 1c, it's obvious that the shear force gives rise. However, we can calculate the value of the shear stress, say at the center, and what its distribution in a cross section is, and that obviously depends on what type of cross section you have. Now again, going back to civil 210, so suppose we've got a simply supported beam with a point load in the center, and then let's suppose that I did 2 cuts there, 1 cut there, 1 cut there. So let's suppose that so I'll just draw that. So on that face there, obviously that goes there. Now on this side here, on the other side of the cut, goes like that. Other side of this cut here, so making our second cut. So the second cut would have to go down like there. The third side would go up like there, and then just continue for the rest of the beam there. Okay, so I'll stick that load on there as my 10 kilonewtons. So I've made my cut. Let's just say it's a symmetrical cross section, so I'll just make an adjustment there. We'll just do that there, so that it's sorry, not a symmetrical cross section. Let's just say that it's a square. The cross section is square, so I'll stick my 10 kilonewtons up there, which you can see, and then I'll put some thickness. I'll put some thickness there. So put some thickness there. So we're saying that if I took the cross section there above AA, then the cross section may look like that, which is about as simple as you can get. So what happens there? Let's now say that I'm taking this bit out here, so I'll just draw that bit out there. So we've got that bit there, and then let's say, for example, that I take another bit out from the center. So this one would be like that with your shear force, and I think I've drawn that wrong there. It's not that I've drawn it wrong, it's I like the stress to be shown working on the face. Yeah, so that's better. But the direction is fine. So we've got that, and then if I take out another bit at the center, so that's obviously 5 kilonewtons, okay, and then up here we've got the air, and then up here we've got the air. And now if I take and try to pronounce this properly, infinitesimal dx by dy, which I could say would be right at the center there. So now let's just draw that, so, and then take that one out, and then I'll call that dx. So you've seen all this before, and then that would be dy, and we would know that there's a stress going up here, and we would know that there's a stress going down there. There must be another shear stress in that direction, and there must be another shear stress in that direction. So the vertical shear stresses, we take our cut, you've got a shear force, and then we've got a distribution of the shear stresses, which allow the top and bottom to be 0. If we went to the center, the distribution, or anywhere else other than near the top or the bottom, and we went to dx and dy, which is infinitesimally small, we would go back to what we understand as our complementary shear stresses. So we need our vertical shear stresses require an equal horizontal shear stress on these parts here, which we can see there, for our dx and dy. So shear is not just about being in the vertical direction. Whatever stress you have, it's the same in the horizontal direction. So it's obvious that the shear stress gives rise to transverse shear stresses, but how can we calculate its value, and what is its distribution in the cross section? And what we'll be seeing is that there must be a horizontal shear stress, and if you take these two, they'll be spinning it around that way, and then if you take these two shear stresses in the horizontal direction, it will be going in the other direction. So these two would make this blob want to spin in the clockwise direction, and then these two obviously have to be in the opposite direction to make it so that it doesn't spin. So they would be in the in the anti-clockwise direction, and the stresses and the stress and the magnitude of the stress must be the same. Okay. So hope that all makes sense, or hope that's a good recap from what Lucas has taught. Furthermore, by extracting a free body diagram from the beam, as we can see here, it can be seen that there must be longitudinal shear stresses also needed to maintain equilibrium when the shear force is present. This may not be obvious at first, but look at the direct stresses acting from left. It's different from the direct stresses acting from right. This means that bending moment changes as one travels along the beam, and so dm by dx is equal to the shear, which is not 0. So the direct stresses acting on the free body from the right has a net resultancy that needs to be balanced, and that leads rise to this horizontal shear stress. So back to our beam here, we know that there's going to be no horizontal shear stress at the top surface because the atmosphere is here. We know that there's going to be no horizontal shear stress at the bottom here, and we could probably guess that the maximum shear stress is going to be along the neutral axis of the section along here. So that's where the shear stress, which we're going to be calculating, must be maximum. So the behavior of a beam made from a stack of planks demonstrates the sliding that will occur between the planks when they are not attached to each other. So right here we've got 1, 2, 3 planks of timber, we're sticking a load on, and each of the plank is going to act by itself. So there is going to be relative sliding. So we can see that here with two planks. Sorry, two. Yeah, okay, so we can see that. Let's just make a correction there, so that we can see the third plank. So we can see, so you can see plane sections are not remaining plane. And we can see that there is relative sliding, which means that each of the individual planks is bending about its own neutral axis. So we've got three planks, and each plank is bending around its own axis and sliding relative to each other, which is why we end up with this distance here at the end. What we might do is we might put some nails through the planks, or we might glue the planks together to prevent this relative sliding. So if the planks were prevented from sliding by connecting them together, for example by using some glue with bonding as you get in timber, their tendency to slide would result in shear stresses being developed at the interfaces, as illustrated in figure 5, which we can see up here. Extending the argument, we postulate that similar shear stresses must exist even if the beam is a fully solid bit of timber or concrete rather than made from planks. So if we've got a solid beam, a solid timber beam, there are going to be shear stresses acting. There are going to be these horizontal shear stresses acting through it even, these need to be calculated. So figure 5 shows how the cross-section tends to distort as a result of the shear strains caused by the shear stresses, whose presence we've just argued needs to be there. So we can argue that it needs to be there from the complementary shear stresses that you would know from Civil 210. Euler-Belluni assumption of the basic engineering beam theory, sigma equals my over I, plane sections remain plane. Which is true in the case of pure bending, but is only approximated when the shear force is present. However, we continue to use this assumption with formulas whose derivations depend on it, such as equation 1, so that we do not normally result in large errors. So that's just about an assumption that we normally use. Plane sections remain plane, sigma equals my over I. And the other assumption, of course, is that when you type into Google deflection of simply supported beam under point load, the equation that Google would give you relates just to the bending stresses. It doesn't relate to the shear stresses, because normally the deformation caused by the shear stresses is very, very small compared to the bending stress. Let me just give a, so we've got a simply supported beam, so I won't bother to show the thickness. And then we've got another one here, like there. So instead of that, I'm going to be applying I'm going to be applying a moment at the end. So let's say that my moment is going to be 100 kilonewton meters, and that's going to be 100 kilonewton meters. And then let's say that that's going to be P, so 100 is equal to PL over 4, where P is the load, so 400 over L is equal to P. So let's just say that that's going to be 4 meters. So I hope I got that right. And that's going to be 4 meters. So, so if that was 400 kilonewton, then we would get a bending moment diagram like that. And we would also get a shear stress distribution, sorry, a shear force diagram like that. Here we apply, and the magnitude of that is going to be, hope I've got that right, 100 kilonewton meters. If I've not got it right, I'm trying to get 100 kilonewton meters there. And then here we've got a bending moment diagram under pure bending. and the bending moment diagram of that would be like that, with that also equal to 100 kilonewton meters. When it comes to the shear force diagram of that case there, the shear force diagram is going to be equal to 0 kilonewtons, because there's going to be no reactions on that side or that side for the pure bending, whereas for this case here there's going to be 200 kilonewtons in terms of the shear force diagram. So all I'm saying is that in this case here, you've got pure bending. So if we take the same bit of planks, even without the adhesives, and so there's no adhesive or there's no screw or nail to prevent them from sliding, and we put it under pure bending, because the shear force is going to be 0, or the vertical and the horizontal shear force is going to be 0, there's going to be no sliding. So when you apply pure bending, that leads to 0 shear, which means that for that case, under pure bending, you don't need any adhesive to prevent your planks from sliding relative to each other, because they wouldn't want to slide relative to each other. So hope that makes sense, but it just shows it's important to get the shear force diagram. So what we have here is, you should be convinced that we know that dm by dx is equal to v. dm by dx is equal to v, or the change of bending is equal to the shear. So here we've got a beam of a rectangular cross section with 2 loads on it, and that would be the bending moment diagram. And unlike here, where the bending moment diagram is constant, there's 0 shear, whereas here there are some gradients, and so there is shear, which generates, I suppose, that bending moment, and you can see the change of bending moment for this dx taken along there. So if you take the bending moment on the left side and on the right side, and the right side is bigger than the left side, you've had a change of bending moment, which means there must be shear, and we can calculate that shear as we will see now. So let's cut the horizontal plane from the neutral axis. So here's our beam there. Doesn't say what the depth is, but it doesn't matter. By symmetry, we would know that would be the neutral axis, where the bending stresses would be 0 from sigma equals my over I. And if you really wanted to, we could say that our y-axis starts from the neutral axis. So let's now take a cut. Let's take a cut, any view from the neutral axis, a distance y from the neutral axis. So there's the neutral axis, and let's just make a cut here. So cut. So we'll just take a cut there. All right, so we'll see that cut here. So we've now made a horizontal cut on the distance y from the neutral axis, isolating the shaded planes, so we can see top of the cut and bottom of the cut. And we can see that the stresses, the bending stresses act there, and we can see the distribution of the bending stresses. So let the cross-sectional area of the shaded piece be denoted by A dash. So we've made our cut an arbitrary distance y from the neutral axis. So our y-axis starts from the neutral axis. We've made this cut here, and there is a direct stress on the left-hand side of the cut, which increases from sigma to sigma, increasing from sigma to sigma plus d sigma equals sigma plus delta sigma divided by over delta x dx at the right hand side. So let's do some equilibrium of these horizontal stresses, because after all, we are trying to calculate these horizontal stresses. We're trying to calculate the horizontal stresses here, which we know must exist because they are in equilibrium with the vertical stress. So the equilibrium of the horizontal stress acting on the isolated body can be written as tau, tau being on how we define the shear stress. So tau times the breadth times dx, integral of sigma dx, sigma dA. Subtract that from what's happening on the other side with the increased stress. That, of course, for equilibrium must be equal to 0. Note that this equation shows the shear stress is required to balance over the area A dash as argued before. So we eliminate all repeated terms and divide by dx. From engineering theory of bending, we know that sigma equals my over I, where y is measured from the neutral axis. So y dash is the distance from the neutral axis to the fibre we calculate the stress for. Do that substitution, tau b is equal to the integral of that. And we also know that following the relationship between bending moment and shear force holds, dm by dx is equal to v. And using the previous equation, tau b is equal to that. And then we come on to this thing called S dash. So S dash is the first moment of area of wherever you've made the cut about the neutral axis. So S dash becomes quite important for calculating the shear stress. So again, let's say simply supported beam with point load of 10 kilonewtons. The reaction would obviously be 5 kilonewtons on both sides. And that's just your beam. You draw your shear force diagram, which is there, and then let's say calculate the shear stresses at there. So what goes into that equation for the V is the 5 kilonewtons. Yeah. So you don't put the 10 kilonewtons into the equation for the shear stress. You put in the 5 because the 5 comes from the shear force diagram. So hopefully that's clear. Now what's S dash? So we've not quite come to the thin walled sections at the moment. So this is a solid rectangular section. And we're saying that our cross-sectional area of, if we did that, we're saying that the cross-sectional area would look something like that, and then that being the neutral axis of the section. And let's suppose that we call that 100 millimeters, and that we call that 200 millimeters. And let's suppose that we wanted to find the shear stress at, say, 50 millimeters away from 50 millimeters away from the neutral axis. So we're putting a cut to calculate the horizontal shear stresses, and that's going to be 50 millimeters away from 50 millimeters away from the neutral axis. So what we would do is I'll draw out the neutral axis, and then I'll draw up the outline of the section, 100 millimeters by 200, and then we want to make our cut 50 millimeters away, which would be along there. So we're making our cut there, and then let's just take the top portion. You can take the bottom portion if you really want to. And S dash then becomes the first moment of area of this area here around the neutral axis. So in this case here, what's the equation for the first moment of area? Well, you can calculate the area, which is going to be 100 times 50, so 100 times 50, and then multiply. So we know the centroid is going to be there, and you just work out what that distance is there, and that would be your first moment of area. So if you're working out the stress, 50 millimeters upwards or downwards from the neutral axis, because it's going to be symmetrical, we're just taking out that area there, work out the area, work out the distance of the centroid of that area to the neutral axis, which is probably going to be 75 millimeters, and multiply that area by the 75 millimeters, and that will give you your S dash, which would tell you what the first moment of area of that is. And then we need to divide it by I times by. By is the breadth of the section, so in the case of a rectangular section, by is constant. So if we were using this one and that was 100 millimeters, then by would just be replaced by 100 millimeters. And then I of a rectangle, so back to the full shape, the I would be 1/12 times the breadth, which is 100, times d cubed. In this case here, it's going to be 200. So hope I've not made a mistake. So that would 1/12 bd cubed, and that would be an equation that you need to remember or commit to memory to do engineering. So that basically tells you how you can calculate the horizontal shear stress at any point by making a cut in the vertical direction. We know that, let's just have a look at this equation again. So if our cut was up here, right at the top, or just underneath the top, then that's going to be 0. So that's going to be 0 because the area would be 0, which would tell you that the distribution right at the top, that would be 0 newtons per millimeter squared. And if you made a cut just a hair's breadth from the bottom, since that area is almost going to be effectively 0, that would tell you that that value is going to be 0 kilonewtons per millimeter squared. And then we can calculate our value up here, which we've done there. And no surprise, if you did the stress at the neutral axis, which would mean you're talking about that blob. So the biggest area times the moment arm, which would be 50, that's going to give you a much higher stress than if your cut was at 50 millimeters away. So your distribution would turn out to be parabolic, as we've actually know from what Lucas has taught you anyway, with the biggest stress, with the biggest horizontal shear stress occurring at the neutral axis in the horizontal direction, and that would be exactly the same as the vertical shear stress. So the above calculations help us to find the longitudinal or horizontal shear. However, we also noted the presence of the vertical shear stress, and we need to calculate those values. And I've already said that when we talked about this, the vertical shear stress is the same as the horizontal shear stress because they're complementary. So the vertical and the horizontal are complementary and they are the same. So to summarize, if there is a shear stress acting in a particular direction at some point in the body, it will also be accompanied by an equal shear stress acting at 90 degrees in such a way that these two stresses do not produce any net moment. And we talked about these two wanting to make this blob twist in the clockwise direction, and these complementary shear stresses wanting to correct that, and so going in the anti-clockwise direction. So no shear stress acting in the particular direction, so there'll no net moment. So example 1, find the distribution of shear stress in a rectangular hollow, in a solid rectangular section. So if you go into the Dropbox, I've already uploaded the solutions. Firstly, some students just want to see the solution. So for those students who just want to see the solution, there's a type solution, which is provided. Some students want to have some commentary. So for those students who want some commentary, I've provided another solution which has full commentary. But let's have a look at the typed out solution first. Find the distribution of shear stress here. So we can make our cut at any arbitrary point y from the neutral axis. So remember that our axis starts at the neutral axis. V is the shear force. S dash is the first moment of area. So we see A for the area, and we see y bar as the distance from the centroid of the area to the neutral axis. So A dash y bar, that's just your S dash, which we saw before. I is 1/12 BD cubed, which we can see there. And then B, the section is not like that. It's got a constant breadth all the way going up. So this section here wouldn't have a constant breadth, but our particular section has a constant breadth because it's rectangular. So B is going to be constant and is not going to be changing as a result of moving up and down the section. So shear force, V from the shear force diagram, A dash is going to be that area there, which is going to be B times D/2. So that distance there, so the whole section is D. So D/2 is going to be that distance there. So D/2 minus Y. So we want to make our cut at a distance Y. So we'll put our axis there. We want to make our cut here, which is a distance Y. So D dash minus Y is going to give you that distance. And now we want to work out the Y bar. So the Y bar is going to be equal to half D/2 plus the Y to give you the Y dash. So if that point there is Y, then we need to go up to the centroid of that area. So that bit is just being added on. And then on the bottom side, I for a rectangle is 1/12 BD cubed, and then the breadth, as we've said, is constant. So from there we can get an equation very quickly. Tau equals that being the shear force. So as tau varies as a square of y parabolically, ranging from a maximum at the neutral axis. So here the horizontal shear stresses or the vertical shear stresses. So we can draw the vertical shear stress if we wanted. So here the vertical shear stress is going to be maximum at the neutral axis, and it's going to be the same as the horizontal shear stress going into the page. So at y equals 0, tau max is equal to 3 3v 2by, putting in 0 of course for the y. So this is 50% or 1.5, the average shear stress. So tau is the total shear force divided by the area times 1/2. So what does that mean? So we've got our beam there with a point load there, and then we know that the shear force diagram of that is going to be that. So I'll say that's 20 kilonewtons. So we know that the shear force diagram is going to be 10 kilonewtons, and it's going to be 10 kilonewtons there. So if we're saying what's the maximum shear stress of that cross section, the maximum shear stress is going to be along the neutral axis. It's going to be along there. So if we had, if we said what's the average shear stress, so that's going up, so that would be going down like there and up like there. So we would say that's 10 kilonewtons. So the average shear stress is equal to the shear force, which would be equal to 10 and divide by B and D, which is the average but we know that the shear stress distribution is actually parabolic, like there. So there's a maximum shear stress, and the maximum shear stress is equal to 1.5 times the average, which would be 10 over BD. So that's all what it's saying. If your cross section is rectangular, work out the shear force, divide it by the cross sectional area to give you the average shear stress, which completely ignores the parabolic nature. Increase that by 50%, and then that would be the maximum shear stress that you would get along the neutral axis. So consider a small cube of material with one face lying on the beam. If the surface is free, okay, so this is just saying what we said before. We've got the air up here, so the shear stress is 0. So we conclude that the shear stress perpendicular to any free surface must be 0. So the shear stress vertical, horizontal at the top and the bottom is 0. So that's the type solution, and Lucas would have also covered a derivation. If you wanted to watch me go through a longer version of that solution, just go to this YouTube link there, so you can get this off the Dropbox. Now, let's move on to question 2. So what's happening in question 2 is that we've no longer got, we're no longer talking about a rectangular section. So that would have been the original cross section, or it could have been the original cross section. But we know that obviously we want to reduce carbon emissions in this world. So we want to make our structures more efficient. And a square shape is not necessarily the most efficient shape, and you can save a lot of material, and therefore you can save a lot of carbon. So come and talk to me about carbon emissions and sustainability if you want to. I'm doing life cycle analyses of buildings at the moment. So we've got a timber beam, and it's made up of 2 sections. So one section is 200 by 50, and the other section is also 200 by 50 millimeters. And what it's saying is that we've glued, so we've glued it along here. It says that the shear force V is equal to 10 kilonewtons, which would mean that if it was being used in a simply supported beam, that would be 20 kilonewtons, reaction of 10 kilonewtons, reaction of 10 kilonewtons there. So we can see that the shear force diagram that thing needs to resist must be 10 kilonewtons. Okay, so don't use 20 in the calculation. I've said that a few times already, so maybe I should stop repeating that. What is the required glue strength? Normally specified as a shear stress. So you could go to our lab and to measure the shear stress of glue. So you could put some, maybe if that was 1 centimeter squared, for example, this bit there, you pull it apart, and then that would, and then the failure load would tell you what the shear stress is. So again, I'm aware Lucas has gone through this already, so you could have a look at Lucas's notes, or there's a solution here which I probably got from Chegg, just to make sure that the guys at Chegg can give the right solutions. So what we can see here is that the first part of the calculation is to work out the position of the neutral axis of our shape there, because we know that wherever the neutral axis is, that's where our axis starts. So that's where our y-axis would be starting. All right, so we need to know the position of the neutral axis. So this bit here says that the position of the neutral axis is 162. So that distance there would be 162.5 millimeters. So if you don't know how to do the calculation, don't worry, I'll talk you through it in the YouTube video. Then you want to work out the second moment of inertia of this thing here. So again, using 1 over 12 BD cubed, calculating it around the neutral axis and using the parallel axis theorem, you can of course work out what I is. So I, he's called it ZZ in the Czech solution, but I would probably call that, in New Zealand we would call that XX. I think if you go to Europe, they'll call it ZZ. So maybe the guy who wrote out the Czech solution comes from Europe. X in Europe is along the length of the member. So X in Europe would be in that axis along the longitudinal axis, which is why I prefer to use terms major and minor, or weak and strong, because then you're not getting confused with different axes, like different sign conventions or different bending moment conventions. Then calculation of the shear stress. So we're calculating the shear stress down there. So obviously we're taking our cut maybe a hair's breadth below the adhesive. So the adhesive could be here, and a hair's breadth below the adhesive would be a good place to take it. So a hair's breadth just below the adhesive would be a good place to do our calculation, not above the adhesive, because you've got a change in breadth. So below, so the adhesive is obviously here, it's not over there, because any adhesive here is doing nothing. So we'll just imagine that we're taking our cut a hair's breadth below the adhesive. So a hair's breadth below the adhesive would turn out to be that here. And then a hair's breadth above the adhesive would give you that bit. Okay, so we'll get rid of that. So, looking at this here, they've worked out what that area would be, because you're making our cut a hair's breadth above the adhesive. We're making our cut, and then we can work out what the shear is, or the first moment of area, which we've got there. Calculate this out here, and then from there we can work out what the stress is. So if you wanted the full solution, again, I've got a YouTube solution, so you can go to these YouTube links here, and you can hear me narrate how these numbers have been calculated, leading rise to the same distribution that what was calculated by the Czech solution. So that handles example number 2. Example number 3. Well, let's talk about shear stresses at the free surface first. But I think we've covered this already, since we're saying that the shear stresses up and bottom must be 0 at the free surface. And then here we introduce the concept of shear flow. So when we talk about a shear flow, we're talking effectively about traction. So the units of the shear flow, so we're used to talking about stresses or shear stresses and the units of the shear stress would be newtons per millimeter squared. So shear flow, so that would be the units of shear flow are force divided by distance. So for the shear flow Q, the units is just a direct conversion from the stress to the flow. Okay, so if you can work out the shear stress, you have the shear flow. And it's normally more convenient to talk about shear flow because when we talk about thin walled sections, such as a lip section down there, we're assuming there's no transverse shear stress going in that direction or that direction or that direction, no transverse shear stress going in these directions here. So why not just multiply your stress by the thickness? So normally in a thin walled section, the whole thing is of constant thickness. So why not just multiply that by the thickness and get rid of the stress and call it something more sensible, which is the shear flow. And then you can start doing some calculations a bit easier. So again, referring to figure 8. So let's go to figure 8. Yep. The stresses on the upper surface generate a total force, dq. If we now calculate the intensity of this force per unit length, we obtain the so-called shear flow. So it's in this book, it's small q. So we've got this. So if you see tau, that's a shear stress, and if you see q, that's a shear flow. And all you can see is that the tau has been multiplied by, in this case, by the breadth, because the breadth of the section is constant. And later on, when we talk about a thin walled section that's been folded around, so suppose this is a bit of metal, suppose this is a steel sheet, and then we've made some folds along the steel sheet to turn it into a channel section. So I'll turn my steel sheet into a channel section like that, so you can see. So I've folded a steel plate to turn it into a channel section, and when we talk about a channel section, it's more convenient to talk about a shear flow that would be flowing around here, and the shear flow is just equal to the shear stress at any point. So the shear stress there multiplied by the thickness, and you can see the units being newtons per millimeter. So the intensity of a force for the beam is we can be expressed in terms of a flow, and this flow would be called small q, and we'll show later on when we come to example 3 how we can use this concept of shear flow to be able to do this calculation here, which I'll talk you through tomorrow. So I think that's it for today, and see you tomorrow.